This video introduces Composites Modeler for Abaqus from SIMULAYT. Composites Modeler, or CMA, complements and extends the powerful ply modelling features that exist in Abaqus CAE by providing proven fibre simulation capabilities and advanced model building, all seamlessly integrated within Abaqus CAE. Furthermore, direct integration with SIMULAYT's layout pipeline allows direct linkage with design and manufacturing functions. CMA provides tools to Abaqus to simulate composites on a ply basis. It includes draping and flat pattern simulation. It also gives a simplified method of adding laminate information for solid elements, and using the layout format, the data is transferable between other applications linking to design and manufacture. Importantly, CMA realistically models the way composites materials are used. The manufacturing constraints and the design intent are reflected in the analysis model. The fibre simulation ensures that unmanufacturable plies cannot be specified right at the beginning of the process. It avoids costly re-engineering late in the development cycle. Manufacturing data is generated to ensure that the final part matches the analysis model. The 4 stages of composites design are as shown. CMA is applied in the transitions from zone to ply models in analysis, and to the output of these into manufacturing. Note the iterative nature of composites design, and CMA assists in this by the ease of transfer of data between the stages. Continuously varying fibre orientations and ply thicknesses can be fed directly to nonlinear implicit and explicit solvers for detailed analysis. The resultant orientation of plies on each element reflects the simulated and actual fibre architecture faithfully. Once installed, CMA is accessible via a tab in the Abaqus CAE interface. The CMA model is based upon the parts available in the CAE model database. One part is selected at a time, and each part will have a separate layout associated with it. The CM model can then be derived from the CAE layups that may have been created within Abaqus, or a blank layout can be created. If a layout file exists for the part, possibly from CATIA v5 via a composites link, this may be imported into this blank layout. This will now be demonstrated on a typical Abaqus part. We have a shell model already in existence, and we can see here we have a part which consists of composite layout information which has previously been created. This is typical Abaqus CAE information and is built along the idea of ply information. We can illustrate these plies by selecting sections off the display menu. And now if we go into the Composites Modeler application, so the CM tab, and selecting the part, there may be multiple parts in the model, but in this case we have a single part, and we're going to create the layout, the Composites Modeler layout, directly from that layout information that existed within that model. That has now created a layout file within the model in which the materials have been transferred. We have all the ply information. There's no offsets in this case, but we also have all the layout information transferred into the Composites Modeler application. This can now be edited as if it was created standalone. As you can see here, here's the table that we could use to edit the part. If we now go back into the Abaqus application, you can see there's some additional information has been created to reflect the fact that we have started Composites Modeler model, and then we can create typical Abaqus sections, composite sections, using that information from within Composites Modeler. We can do that fairly simply here, just accepting the defaults, and as you can see, because we had sections displayed, we can see the extent of those, and through the menu here, the browser tree, you can see all those plies have been transferred into a number of sections. Now using the same shell mesh, but without the CAE layout information being available to us, and no sections already created, we can create a Composites Modeler model, or create a layout directly on this part. we give it an appropriate name, and we have blank information here in terms of materials, plies, etc. So first we must ensure that we have ply materials available. This is essentially having the fabric on a roll ready to be placed. This references analysis materials created in CAE. Then each ply is created with reference to the part mesh and the materials created previously. In creating the laminate, we may need to apply an offset, for instance if the geometry represents the tool surface rather than the mid-plane. And then a layup is needed to define the sequence of application of these plies. This will be used to create the analysis properties. We can now illustrate this using the blank layout file that we've created previously. And we're going to build this on the shell mesh, as you can see on this model. The first thing we need to do is to define the materials for use. So if we create a new material, give it an appropriate name for reference in the layup, and then we can select the appropriate analysis materials that have been created in Abaqus CAE. We have a number of material types, which basically are the draping algorithms, and also give the material a particular thickness, and also we have the maximum strain information, which is going to limit the shear of that particular material. You can see we've now created that material, and now we look at the definition of plies. So as I say, the plies is the area of coverage, and we need to give each one a reference name. We can also use the drop-down list to select the appropriate layout material, and we can either use the material algorithm which we selected, or we can use a projected one. We then select the area of coverage. In this case we're selecting all the elements for this surface. We need a reference coordinate system, the x-axis being the direction, the reference angle, and the z direction being the application angle of the ply. We've also now selected a start point, which is the first point of application, so you can see now we have in blue the reference direction, and in green the application direction at that start point. And we're using a 0-degree angle to show our plies, and to do a preview you can see the fibre angles. Changing this to 45, you can see the result there, resulting fibre angles in blue, and in red is the ply extents covering the whole of the surfaces. We can make copies by using the clone, so if we wanted to have the same coverage but at different angles, it's fairly easy to do with the clone function. So now we have two plies created, one at 0 degrees, one at 45 degrees. And what we can then do is to look at those plies. We can verify what we want. We've got a number of visualization tools shown down here on the bottom left. So what we'll do is initially we'll just select those, or deselect all those, just to show the effects of them. So now, if you like, we have a blank image, and we're going to select ply 1, and we can show the elements that are covered by that ply. The next button shows the application direction and the reference angle. Then we have the ply boundaries, and now you can see on the individual elements the fibre directions are shown. If we zoom in a little bit closer, you can see the effects of the curvature. So we switch between the 45, and we can now see that the fibre angles are clearly illustrated. We turn off the individual elements and just looking at the fibre visualization, and we switch back to the 0-degree ply again just for visual reference. And also we can switch on the display of the flat pattern, which is created and stored with the layout file as well. The next object is the offsets, which, as I mentioned, is basically saying whether or not the plies are built on one side of those surfaces or whether it's a mid-plane. Give an appropriate name again. Pick the region for which this offset will apply. We've actually selected the whole of the surfaces again. We need to select a coordinate system, again for the same idea that the z direction is the direction of the offset. A seed point at which to apply that offset, the initial offset, the direction,